Previously, we talked about probabilities and statistics. Now, we're going to talk about some types of probabilities and some rules on the probabilities. Okay, first one is about marginal, joint, and conditional probabilities. And to explain these probabilities, let's take some example. So, for example, let's assume that we have n samples with different colors and the size. Okay, so we have three different size here, and then we have five different colors. Okay, and then in total we have n samples, but in this each cell has the number of cases. So nij is actually the number of this specific case. Okay, so let's say this one is a small size, and this one is a medium and a large, and this one is red and blue and green and yellow and black. Okay, so n sub 1 2 means the number of the samples with the blue in middle size. Okay, and what is the marginal and joint and conditional probabilities? Okay, first, the marginal probability is about one variable. In this case, we have two variables, x and y, but marginal probability is all about one variable, so p of x or p of y. Okay, p of x, when we calculate probability of x, then we don't care the y. And when we are interested in p of y, then we don't care x. Okay, so if in this case probability of x, it means something like p of x is blue. Okay, or p of x is green. So we are interested in these kind of probabilities. So let's talk about one specific case. In this case, we have n1 2 n2 2 n2 3. So c, we have to calculate c2, which is n1 2 plus n2 2 plus n2 3. Okay, so we can get this number, and the ratio of this is actually a probability of probability that x is blue. Okay, so in this case, we don't care the size of the samples. And the n is actually sum of all the samples from the cells. Okay, then next one is joint probability. Joint probabilities is actually the probability of a specific cell like this. So when x is some specific color and y is some specific size, then what is the probability of that case? And that case, the probability of that case can be calculated based on this ratio of n sub ij to n. Okay, I think this is really trivial. I think you understand what I mean by this, but you have to be familiar with these terminologies, marginal probability and joint probability. And the conditional probability is something like this. We're interested in the probability of y given a specific x, or the other way around. Okay, so we are interested in some specific some specific variable given a condition on the other variable. So in this case, for example, we are interested in the probability of small samples when the color is blue. Okay, so then we're interested in this. Okay, the color is blue, and then in these samples, then what is the probability of small samples? Okay, so in that case, that is a ratio of n sub ij, okay, and to c sub I. So c sub I is actually total number of samples in this condition. And given this condition, then we are interested in in the number of these samples or this sample. Okay, that is conditional probability. And there are a couple of rules on probabilities. First, the sum rule. So P of X is actually a marginal probability, and this marginal probability can be obtained by these sum rules. So this one is a joint probability, and given this joint probability, then if we sum over all the cases, all the y's, then this one is actually P of X. Okay, and we actually we can see how it works in these equations. P of X, the probability that P is a specific color, then that is actually C sub I over N, and that can be obtained by this. Actually, Ci is actually sum of this one. Okay, and then N sub ij is N over N sub ij is actually P of xi and yj. Okay, so N goes in here, and we can make a ratio inside of this summation. Then we can replace that based on this one. So we got this one. Okay, so this one is actually a marginal probability, and this one is a joint probability. And the next rule is product rule, and P of x, y, joint probability is actually conditional probability times marginal probability. Okay, so we can see this rule based on this equation. So probability of x and y is actually this one is a joint probability, so we know this can be obtained by this ratio. And then we can decompose this one into two terms, like this one and this one. We multiply Ci in the numerator and denominator. So basically we have this equality. Okay, then if we look at this part, that is actually conditional probability, and this one is actually marginal probability. So we got that. Okay. And there are a couple of more rules and terminologies about the probability. First one is independence. So independence is really important in the probability, so you have to understand what this equation means. So if x and y are independent, probabilistically independent. Long time ago, we talked about linear independence, okay, in the linear algebra, and this independence has nothing to do with those kind of linear independence. So probabilistically, random variable x and y are independent if this. So P of x is the same as P of x given y, then x and y are independent. And this one is actually same as this one. Okay, so you can prove that by yourself. And let's try to understand what this equation means. Okay, so the first term, P of x, is actually probability of x, and this one says the probability of x given y. So when we have a specific y, then we're interested in the probability of x given that condition. But this equation says, this equality says, y has nothing to do with the probability of x. So no matter what kind of y we have, no matter what kind of condition we have on a variable y, P of x given y is P of x. So in this term, we don't have y. So in this term, we have y. So y has nothing to do with x. So x and y are independent. Okay. Actually, you can check some TOEIC cases by yourself. Okay, and as I said, this equality is the same as this equality, and the conditional independence is almost the same as just independence except this term z. So let's just compare these two equations. In this term we don't have given z part, but now we have given z, and this we add given z, and in this equation we add given z, in this equation we add given z and given z. So conditional independence means the x and y are independent given z. Okay, so that's conditional independence. This independence, it has some condition which is z. Okay, and the next one is correlation. So we might have this notation or this notation. These are notations, and this correlation can be defined by the covariance of x and y divided by the variance, standard deviation of x and standard deviation of y. Okay, and then we can actually rewrite this covariance in this way. Okay, and then we want to talk about uncorrelatedness. So this correlation is actually, it says how much x and y are correlated. What do you mean by this correlation? So let's say we have a two variable, scalar variable x and y, and when we get some samples from x and y, then if the sample looks like this, okay, then there's no correlation between x and y. Okay, if we have samples like this, then x and y has no correlation. When we know something about x, let's say okay, when x is this, then we have no idea about y. So x doesn't tell us anything about y. Okay, if we know the value of y, so let's say y value is here, but it doesn't say anything about x, so they are uncorrelated. But if the samples look like this, okay, then we have a strong correlation between x and y. What do you mean? What does that mean? If we know the value of x, so let's say x is around here, then we can say pretty much about y. If x is around here, then we can say pretty much about y. Okay, so we have a strong correlation. What if we have something like these samples? Then they have a strong correlation, but in a negative way. So we have actually strong negative correlation. Okay. And if it is uncorrelated, if x and y are uncorrelated, then they have a zero covariance. We can see this really easily. Okay, so this one is a zero. Uncorrelated means correlation of x and y is a zero. If this is zero, then covariance should be zero. That's simple. If a covariance has a zero, then the correlation should be zero. Okay. So since covariance is zero, then this should be zero. Then we can rewrite the covariance. Then the covariance can be rewritten by this. Then when the covariance is zero, then we get this one. Okay, so we have similar equation here. Okay, if x and y are independent, then the p of xy is p of x times p of y. If xy are uncorrelated, then expectation of xy is is expectation of x times expectation of y. So they look similar. Okay. So this is actually related to the statistics of distribution. Okay. In the previous lecture, I talked about the moments and statistics, and when we know when we have a probability distributions, then we can calculate all the statistics or all the moments. Okay. Then if we know all the moments from the first moment to infinite moment, then we can define the probability. But usually the probability distribution is really complicated, so usually we use the first moment and second moment. Sometimes we can use a third and fourth. So we can use mean and variance, sometimes skewness and kurtosis. Okay, so this is about the second moment. So if we have this independence equation, then definitely x and y are uncorrelated. So this one implies this one, but not the other way around. So even when x and y are uncorrelated, but still they might be dependent. Okay, so this one doesn't guarantee this one. Okay, and we can prove that if two variables are independent, then they're uncorrelated. We can prove that. You can try that by yourself. And how about the other way around? As I said, even when they are uncorrelated, sometimes the two variables are dependent. Okay. Okay, and the next rule is probability chain rule. Okay. Chain rule is actually generalization of simple product rule. In the simple product rule, we already observed this equality. Okay, probability of joint probability of these two variables is actually marginal probability times condition probability. So we already talked about this product rule, and the chain rule actually generalize into n variables. So probability of these variables is actually probability of the first variable times probability of x2 given x1. So conditional probability times another conditional variable and another conditional variable like this. And the order is not that important. We can change the order. Like it could be p of xn times p of xn minus 1 given xn, etc. Okay, we can change the order. Okay, but if we start x sub 1, then the next term should be the probability of some variable like p of x1, p of x3 given x1. Okay, then p of x, let's say 7 given x1 and x3, because we have x1 and x3, so x1 and x3 should be the condition of this probability, times p of, let's say, x5 given x1, x3 and x7, etc. Okay, so the order means nothing here as long as we keep these kind of patterns. Okay, and we actually use this chain rule a lot, especially in language model. So think about a sentence with the word sequence. Then the sentence can be represented in this way. This is a sentence and with n words. So this is a sequence of n words. Then the probability of a specific sentence can be rewritten based on the chain rule in this way. So first word, and this probably says the probability of the second word given the first word. Okay, and this one says the probability of the third word given the first two words. Okay. And this one says the probability of the last word given all the previous words. So we can summarize this equation. We can rewrite in this way. Okay, now let's talk about the Bayes theorem or Bayes rule. And the Bayes rule is actually a really popular rule here. But it's really simple. P of y given x is P of x given y times P of y over P of x. Okay, and the P of x can be rewritten in this way. If we rewrite this one slightly, then you can see this P y given x times P of x. P of this one can move to the left side of the equation, is P of x given y times P of y. Okay, look at this one. This one is a conditional probability and this one is marginal probability. So this one is actually P of y and x, joint probability of y and x. And also this one is also a P of x and y, joint probability of x and y. So these ones are the same. Okay, so this one is really trivial equation, but it was proposed by Thomas Bayes long time ago. And this term is really important in machine learning. We have lots of problem because of this term. Okay, so P of x is a summation of this conditional probability times marginal probability. And most of the time, this sum is not possible most of the time. Okay, so when x is data and y is parameter, then Bayes rule can be interpreted in this way: posterior and likelihood and prior. Because we don't have P of x, as I said, P of x is really complicated, so most of the time it's not possible to get P of x. So without P of x, we have a proportional symbol here instead of equality. So this one is posterior, and this one is a likelihood, and this one is a prior. Okay, and the Bayes rule actually presents the transformation process of our belief. So y is parameter. So without the data, we already have some probability about the parameter. Okay, then look at this one, posterior. You don't understand what this prior and posterior mean. Prior means before something, and posterior means after something. So this one says, before looking at any data samples, I have some faith about y. I have a probability of y. And when we look at this data x, then my faith about y has changed by observing x. So probability of y given x and probability of y. So the difference between these two is this term, given x. Given data, we have changed our probability of y. Okay, so subjective belief on y changes with x. Usually, science works in this way. Let's assume that you think the earth is flat and you have some confidence about that. If you have 100% confidence about your thought that the earth is flat, then when you observe any data set, data samples, then you don't change your mind because you are 100% sure. But if you have like 90% certainty, you're confident about that fact, 90%, then you can update your thought, your faith about the fact. Okay, so whenever we observe some data samples, evidence, then we can change our mind from P of y to P of y given x. So gradually we can change our thought. So if you're confident about the statement that the earth is flat, 90% you're confident, then whenever you observe some data samples, evidence, then gradually you can move from 90% to 80%, 70%. Finally, at some point, then you can say, I don't believe that the earth is flat anymore. Okay, so that's how science works. And John Keynes, who is a famous economist, said, when the facts change, I change my mind. That's how we do science. Okay, now let's talk about learning in Bayes rule. And as I said a long time ago, learning is nothing but to update our confidence from prior to posterior. And the key factor is likelihood, which is based on data. Okay, and in the prior, we don't have data observation, but in the posterior, the probability is actually a condition probability, and the condition is on the data sample. And the key factor is likelihood. Likelihood is actually the probability of the data sample. So in this equation, this one is likelihood, this one is prior, and this one is posterior. And let's assume a model with parameter theta, and when we experience with data sample d, then we change our thought on the theta. And as I said, p of d can be obtained based on this integral or summation if it is a discrete. And the marginalization of the whole primary space is most of cases is not possible. It's not possible. That's the problem. That's the headache in machine learning. Okay, to understand Bayes rule, let's take one example from this book. Okay, and I put this Bayes rule here. And let's say we're interested in the probability of breast cancer when X-ray is positive under age 40. Okay, then we can actually use this equation exactly here. So breast cancer BC corresponds to Y, and X-ray positive X-ray corresponds to X. So P of X given Y is this one, and P of Y is this one. And then P of X is actually summation of P of, this term is exactly the same as this one. Okay, so we have to rewrite, we have to use this term and this term. In this case, Y is changing, okay? So in this equation, Y is BC. It is a specific case. And when Y is BC, then we have this term in this summation. When Y is not BC, then we have this term. Okay, so we have a summation here. And again, this one is corresponding to P of XP. This summation is actually corresponding to P of XP. Okay, so now we have a Bayes rule for this case. Then let's actually use some specific numbers. Let's say if P of BC is 0.01, which means just 1%, okay? So in general, the probability that you are diagnosed with cancer, breast cancer, is 1% if you are under age 40, okay? So when you are younger than 40, then without any data, okay, then the probability of breast cancer is just 1%, okay? And the probability that X-ray is positive, even when you don't have breast cancer, is 0.1, which is 10%. So we have 10% error in X-ray. And and the probability of X-ray probability that X-ray is positive given breast cancer is 75%. So even when you have breast cancer, 25% it will not have a positive X-ray. So we have some error here. Okay, so error rate is 25%. Then let's calculate this probability of breast cancer given a positive X-ray. So this is what we're interested in this case. So if we put all these numbers in these equations, okay, so we already have this equation. So if we put all the numbers to this equation, then we get 7%. Okay, so the probability that you have a cancer, breast cancer, when the X-ray is positive is just 7%. So this one is very low even when P of X-ray positive is high. Okay, it means it is recommended not to test unless the test is really accurate. So that's why you are under 40. Then you don't have to take this breast cancer X-ray test. It's based on base rule. And when you read some textbooks or some papers, then you might meet these terminologies, Bayesian and frequentist. And there's a big difference between these two people. Bayesian means the people who are following Bayes kind of approach, and frequentist frequentists are the people who follow this Ronald Fisher's approach. And what is the big difference between these two schools? Okay, the Bayesian thinks the parameters are updated. Parameters are supposed to be updated. Okay, and the parameters actually represented probabilistically. But frequentist says a parameter is fixed. Think about the dice or coin. Okay, there is a coin and with head and tail. Okay, when you toss a coin, then you will see head or tail. Okay, but these frequentists believe that this parameter, the probability of head is fixed. And we are just observing some specific example, which could be head or tail. Okay, but still, they believe this parameter is fixed. But Bayesian people believe that this parameter is moving, this is changing, and this is not fixed number, is probabilistically represented. And in Bayesian approach, there is a prior. Even before data observation, we have some thoughts on the parameter. Okay, we believe something even before the data observation. But in the frequentist, there is no such a thing. Without the data, no nothing. We don't have prior information. And to Bayesian people, data is fixed. If you have head from coin toss, if you have a head, yes, it is data. It is true data. Okay, if you have a tail, yes, that's true data. But to frequentist, it's random samples. When you have some samples, head or tail, but yes, that's true samples, but they don't actually represent the true parameter. Okay, and if we have a lot of enough data samples, then they will converge to true parameters. And usually we take Bayesian approach when we diagnose some disease. Okay, think about this one. When we have some experiment values like blood pressure or some temperature or some things, we observe some phenomena about a patient, then This probability of cancer is not fixed. Okay, we are actually exploring the possibility of cancer. Okay, but when it comes to dice or coin, then the frequentist approach might be much convenient because there is a coin and there is a fixed parameter for the probability of head. Okay, it's fixed. Then we observe some samples. Then that approach might be easier. Okay, and in Bayesian approach, we are always interested in posterior, but frequentists they're interested in this likelihood. Again, posterior includes likelihood, and so in machine learning, a lot of algorithms and approaches are based on this Bayesian approach.